All right, we are into chapter 9. This is perhaps the most important chapter in all of statistics. It deals with significance testing. As we talked about in the last chapter, inference related statistics with confidence intervals and significance tests is probably the most important aspect of the course. At the end of every study, at the end of every experiment, there's some type of confidence interval or significance test that's run to determine whether or not you have evidence of whatever you're trying to find. So let's take a look at this. We're going to start by looking at a case study related to body temperature. So if we take a look at this data that we have here, so we have this gentleman who believes that the actual average temperature is not 98.6 degrees. So what he did is he went out and he collected an oral temperature reading for each of 130 randomly chosen 18 to 40-year-olds. And he's showing his data in a dot plot that's shown here. The blue line represents 98.6 degrees, which is that kind of temperature that we all have been told growing up is the average body temperature. And he believes that it's less than 98.6 degrees, okay? Or it's different than 98.6 degrees, whatever he's trying to prove. So if we take a look at his data here and we find the average or his sample mean, we find that it's 98.25 degrees. Standard deviation is 0.73 degrees Fahrenheit. In addition, 62.3% of the temperature readings were less than 98.6 degrees. So this Alan Shoemaker, he's gone out, he's collected his data, and this is what he's found. And now what we do as statisticians is we say, okay, based on this information, the sample size of 130, a sample mean of 98.25, a sample standard deviation of 0.73, is that strong enough evidence to prove that the actual body temperature of humans is, for example, less than 98.6? Is this strong enough evidence? Does that sample mean, given that sample size and that sample standard deviation, provide strong enough evidence to make that claim? And that's what we do in statistics. That's what running a significance test is all about. So what are two possible explanations as to why we got a sample mean of 98.25 instead of 98.6? Well, the first explanation is that the actual population mean really isn't 98.6. The actual population mean maybe is less than that. Because if it was less than that, it would be more likely that we would get a sample mean of 98.25. The other explanation is that it really is 98.6 and that we observed a sample mean of 98.25 just by random chance, just by chance alone. And this goes back to the idea of, okay, just because your actual mean is 98.6, when I take a sample of 130 or 140 people, however many I took, I'm not going to get 98.6 every single time in my sample mean. There's going to be that sampling variability. But what we have to determine is, how likely is it to have gotten this sample mean if the actual mean is 98.6? What are the chances of getting that? And that probability is what's going to be used to answer that question. So one of these two things are true. Either the population mean really is 98.6 and we just got this by chance, or the population mean is actually less than 98.6, and that's what we have to determine. By that same reasoning, we can answer the question of, okay, why did we get a p-hat of 62.3% instead of 50-50? We would think that 50% should be above 98.6 and 50% below. Well, either the actual proportion of people with temps below 98.6 is more than 50%, or we just happen to get this by chance alone. So whether you're dealing with proportions or you're dealing with mean type problems, you want to go through that same concept and that same idea. There's two things that could happen. Either this is true and we just got a sample mean or proportion by chance, or it's not true and we have to kind of assess our claim about the actual mean or the actual proportion value. We're going to work through that next example in class, so we don't have to go through that one now. But let's continue on. So when we're creating these studies, and at the end, we have these two hypotheses that are referred to as the null hypothesis and the alternative hypothesis. We label the null hypothesis as H sub 0. H sub 0 is our null hypothesis. We label the alternative hypothesis as H sub A. Okay, so we have the null hypothesis, HO, or H sub 0, and the alternative hypothesis, H sub A. The null hypothesis is our original claim. It's our statement of equality. Your null hypothesis will always, always be equal to. The alternative hypothesis is your new claim, what you're trying to find evidence of. And it can either be a less than, a greater than, greater than, a less than, or a not equal to. So your null hypothesis will always be equal to, and then your alternative has the option of those three different things there. So if we think back to the example that we were just looking at with our body temperature and so on and so forth, our null hypothesis for that particular example would have been HO, and then we always used a population parameter. So don't just say equals 98.6. What is equal to 98.6? In this case, mu is equal to 98.6. So that's what's initially thought to be true. It's always going to be an equal to. In this case, mu is equal to 98.6. Well, what does this guy think? This guy thinks that, and this is our alternative hypothesis, which can either be less than, a greater than, a less than, or not equal to. In this case, he thinks that it's actually less than that. He thinks that the actual body temperature, actual mean body temperature, is less than 98.6. So that's how you're going to be writing your null and your alternative hypotheses. Always using some type of population parameter, most frequently mu or p. You never, ever, ever use x bar or p hat. And then make sure your null hypothesis is always equal to, and your alternative hypothesis can be either a greater than, a less than, or not equal to, depending on what you're trying to find evidence of. Again, we don't use x bar or p hat because we know what we got in our sample. We know our sample mean was less than 98.6. The question is it strong enough evidence based on my sample of 100 and whatever it was, 130 people? Is that enough? Is that far enough away? Is it too crazy of a result, or is it crazy enough to say that this is definitely not true? And that's what a significance test is all about. We'll look at these two examples in class. Let's head down to the bottom of the page, which talks about the difference between a one-sided and a two-sided alternative hypothesis. So as I said, your alternative can either be less than, greater than, or not equal to. A one-sided test represents a less than or a greater than alternative hypothesis because you're only proving in one direction. I think that the actual mean temperature is less than 98.6. I'm only proving to the left, less than. So your null hypothesis would be equal to. Your alternative hypothesis would be either a greater than or a less than, depending on what you're trying to prove. So mu is equal to 98.6, mu is less than 98.6, or maybe you think it's greater than 98.6. How do you decide whether to do a one-sided, which is less than or greater than, or a two-sided, which is not equal to? It's all about the context. Read the question. Are they saying, do we have evidence that the mean temperature is not 98.6, or is different, or has changed? In which case it would be two-sided and not equal to. Or are they saying more, less, increase, decrease, where they're specifically trying to find evidence in one direction? So it's all about what the question is asking and what you're trying to find evidence of. So make sure that you're reading the question. So once you've got your hypotheses, I said the key thing here is finding that thing, which is what's called a p-value, that will determine whether or not we have evidence of the alternative. So what is a p-value? A p-value is a very, 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 very important thing that many people struggle to understand and define. What a p-value tells you is the probability of obtaining a sample statistic at least as extreme as the one observed, given that the null hypothesis is actually true. So make sure that you have this definition down, and then we'll talk about exactly what that definition means. I'm going to go back to my previous example dealing with our body temperature. So I'll give you a second in case you need to write that down. So if we go back to our example here, where our null hypothesis was mu is equal to 98.6 and our alternative was mu is less than 98.6, keep in mind that we got a sample mean here of 98.25. Now, I'm going to quickly calculate the corresponding p-value for this test. Now, you at this point don't know how to do this, but I do. So the corresponding p-value here is equal to approximately 0.000001. So it's a really, really, really low p-value. And what this p-value is saying is it's saying, okay, if we assume that the actual mean is 98.6, we're assuming that the null hypothesis is true. There is a 0.000001 probability of obtaining a sample mean of 98.25 or less. Okay? That's what it's telling us. Basically, there's almost no chance of getting this sample mean or something more extreme, in this case, or something less, if the actual mean is 98.6. Now, what does that tell us? That tells us one of two things. Either we've gotten this really, really, really weird sample, or this is really not true. The null hypothesis is really not true, and the actual mean is really less than 98.6. So this p-value is crucial in determining if we have evidence of the alternative, which is what we're trying to prove. In this case, a p-value being really, really low, because remember, a p-value in an over, and this is a way oversimplified version, the p-value says the probability of getting this in your sample if this is true. Well, it's telling you there's basically no chance that you would get this if this is true, and we got this, so then the null hypothesis is not true, okay? And we have evidence of the alternative. So what do? All right? What we do is we take that p-value and we make a conclusion. If the p-value is low, and this is one of the most important sayings in statistics, p-value low, reject the hoe. Reject the null hypothesis. You'll never forget it. P-value low, reject the hoe. What does that mean? That means if our p-value is low, and we'll talk about what low means, you reject the null hypothesis. So you're saying, null hypothesis, you're out, and we have evidence that the alternative is true. So this is a very low p-value. In that case, we would reject the null hypothesis. Null is out, and we would have evidence. Let me throw an A there. Should be the alternative. We have evidence then that the alternative is true. So we have evidence that the actual mean is less than 98.6. Now, if the null hypothesis or the p-value is not low, the p-value is high, we fail to reject the null hypothesis. Well, what does that mean? That means we never accept the null hypothesis. So we don't say, okay, yes, it is true. The mean is equal to 98.6. We just kind of say, nah, I'm not sure, can't reject this. And you write your conclusion in terms of the alternative. So in this case, we would say we do not have evidence that the actual mean is less than 98.6. So your conclusion should always be written in terms of the alternative hypothesis. The key thing is here that you never, ever accept the hoe. Never accept the null hypothesis. It's a life lesson. We can reject the hoe, we can reject the null hypothesis and say we have convincing evidence of the alternative. We can fail to reject the null hypothesis, in which case we do not have evidence of the alternative, But we never can prove that statement of equality in the null hypothesis. You never accept the hoe. So the most common errors that we see are accepting the null hypothesis and then not linking your p-value to the conclusion. The p-value is key. It is the most important thing. It tells you whether to reject or fail to reject the null hypothesis. So we said p-value low, reject the hoe. Well, what do we determine? How do we determine what is a low p-value? Well, that thing that we use to determine a low p-value is called a significance level. Okay, we define it by the Greek lowercase letter alpha as seen here. The most common significance level that's used is 0.05. So basically what we're saying is if it happens less than 0.05% of the time, or 0.05, aka if your p-value is below 0.05, it's deemed too rare that the null could be true, and therefore we have evidence of the alternative. So you're always going to be taking that p-value and comparing it to alpha, okay? Comparing it to the significance level. So a p-value low means that your p-value is less than alpha. A p-value being high means that your p-value is greater than or equal to alpha. So it's always that comparison of your p-value to your significance level that's most important. P-value low, reject the hoe. You have evidence of the alternative. We're saying there's such a small chance that this null could be true based on our sample data that we have evidence of the alternative. P-value high, not accepting the null, just saying could be true, but I don't have evidence of the alternative. We deem the results what's called statistically significant if our p-value is low, if we have evidence of the alternative and we can reject that value there. We can reject, the null hypothesis. Our p-value is less than the significance level. Let's head down to the bottom of the page. What should be considered when choosing a significance level? So how do we determine? There are different ones. Sometimes you'll see 0.1, sometimes you'll see 0.01, most commonly 0.05. We want to think of how strong we want our evidence to be. Okay, if we lower that significance level, meaning we get it closer to 0, make it 0.01, that will strengthen our evidence because we have less of a chance of rejecting the null. Similarly, we want to think of the consequences of rejecting the null hypothesis when we're choosing our significance level. In statistics, if they don't give you one, we use 0.05. It is the most common significance level to use. Final thing in this lesson deals with type 1 and type 2 errors. So we want to start by thinking about like a jury trial and what two types of errors a jury could make. The first one is that they convict an innocent person. So when you're thinking about errors, you want to always think about what did you do and what's the truth? Well, the truth is that the person is innocent and we convicted them. We say go to jail. The other error you could make is failing to convict a guilty person. AKA, we're saying you're free, you're innocent, but in reality, the person really is guilty. In statistics, we have this same idea in significance testing. We have what's called a type 1 and a type 2 error. And depending on the type of problem, the context that's related, it depends on which type of error could be worse to make. So a type 1 error, you always want to think to yourself, what did we do and what's true in reality? In a type 1 error, we rejected the null hypothesis and claimed the alternative is true, while in reality, the null is actually true. So you've made an error. So if we go back to our last example that we've been dealing with, we think back, a type 1 error, we would say, okay, I rejected the null hypothesis. I said that the actual mean was less than 98.6, the actual mean temperature. That's what we said we had evidence. In reality, that was wrong. And the actual mean really is equal to 98.6. So in describing a type 1 and a type 2 error, you always want to say to yourself, what did I do? What's true in reality? Type 1, I rejected the null. I said I had evidence that the actual mean was less than 98.6, but in reality, it's not. Okay? A type 2 error, and the way you remember it, Type 2 failed to. So type 2 error failed to reject. We failed to reject the null hypothesis. We did not have evidence of the alternative, but in reality, the alternative really is true. So you want to think about what conclusion you made and then what is actually true. So if we go back to our example, a type 2 error here would be saying, okay, I failed to reject the null hypothesis. I do not have convincing evidence that the mean temperature is less than 98.6. That was my conclusion. That was wrong. So in reality, the mean really should have been, or really is, less than 98.6. So depending on what you got on your p-value, in a given situation, you're only going to have committed one of these types of errors. In this example, we may have committed a type 1 error because our conclusion was to reject the null hypothesis and have convincing evidence of the alternative. And again, you always want to think to yourself, what did I do? What's true in reality? So the probability of a type 1 error is equal to the significance level. So whatever your significance level is, alpha, is equal to the probability of a type 1 error occurring. To reduce the probability of a type 1 error, we can reduce the significance level. However, in turn, this is going to increase the probability of a type 2 error. So it's that balancing act there when we're dealing with both of these types of errors. And as I said, and this might be a little kind of helpful thing for you to write down when you're describing type 1 and type 2 errors. Type 1, think about what did we say, what's true in reality. Same thing for type 2. So again, in a type 1, we said null hypothesis, you're wrong. We have evidence that the alternative is true. The reality is really the null is true. In a type 2 error, we didn't accept the null. We just said we don't have evidence of the alternative, but in reality, the alternative hypothesis really is true. So a lot of stuff here. We will recap all of this in class, but hopefully I've laid some of the foundation for you to have an understanding of where we're headed with significance testing, because it's one of the most important things in all of statistics. I'll see you guys in class.